Hello, and welcome to Physics Review Videos, Unit 9, Sound and Light. Today's topic, light. Light is a particle and a wave. This is something called the dual property of light. In general, what we're going to refer to as light as a particle, the key thing is just knowing that this particle of light is called a photon. So it's a packet or particle of light that's transferring this energy. Light, however, can be viewed as a wave, and that's what we're going to focus on today. Light itself acts as a transverse wave, but actually two transverse waves traveling perpendicular to one another. A wave of the electric field and a wave of the magnetic field. Since it's these two together, we can refer to this as the electromagnetic wave, or the electromagnetic spectrum, or EM. However, something else interesting occurs with light. The speed of light is actually constant. Now, it's constant in a vacuum. When we say in a vacuum, we're really just referring to something like in outer space or in air. We're referring to where there is no real particles around to slow it down. Now, in general, when we're saying vacuum, we really do mean space with nothing in there. However, light traveling through the atmosphere, we're going to treat very similar to this speed. Now, the formula for the speed of the wave is velocity is frequency times wavelength. Now, V we know stands for velocity, F stands for frequency, but a quick reminder, this upside down Y, lambda, is what we're using to represent wavelength. Now, since the velocity is constant, we're going to give it a very unique symbol. The symbol is going to be C. C is going to stand for the speed of light in the vacuum. And that speed is a very specific number, 3 times 10 to the 8th meters per second. In a word problem, or a problem dealing with the speed of light, if we are talking about speed in a vacuum, that number will not be given to you in the problem. It is going to be assumed that you know that. So please make sure you know that number. If we rearrange the formula then with this given value, we would say C is equal to F times lambda, or speed of light is equal to frequency times wavelength. Since the speed is constant, this means frequency and wavelength are the properties or the variables that will change. Now, when we're talking about light, you're probably going to think about the type of light that your eyes can detect. Your eyes can actually detect only a very small amount of what you refer to as light, but we're going to expand to call this electromagnetic spectrum. Now, when you think about light, you probably know that black is actually the absence of any light. White is the combination of all light. And when we say all light, we mean all visible light, which is this portion right here in the spectrum. If you notice, these colors of the rainbow, this visible spectrum, is actually only a small sliver of this very large wavelength on the bottom. This big wave on the bottom, this is going to be our electromagnetic spectrum. And visible light, the part your eyes can see, is a very limited portion of this. Now, our color spectrum, you can think of as Roy G. Biv, or red, orange, yellow, green, blue, indigo, violet. On the red side of the spectrum, these are going to have longer wavelengths. So longer wavelength light, your eyes are going to see as red. As it gets shorter and shorter, it's going down that Roy G. Biv kind of rainbow. And so by the time you get to the other side where violet is, the wavelengths are going to be much shorter. Now, if you look, this part, again, is a very small part of this full spectrum. So we want to expand in either direction. So let's start with red. Red is at the very end of the visible spectrum that you can see. Just past red, the first type of light that's invisible to your eyes is infrared light. Now, infrared we can refer to as light, but again, we can also call this electromagnetic or EM radiation or an electromagnetic wave. So this infrared type of light or radiation, this is just outside your field of vision. This is also the type of wavelengths that are given off by heat or temperature or kind of heated up objects. So as you go past red, we're going to enter into the infrared spectrum. If the wavelengths keep getting wider and wider, so here we have our wavelengths, but here they're much further apart. As they get further and further apart, we're going to get into the field of microwaves. So microwaves, we want to think about, are a different color of light, one much further away from what you can see. And if you go even further than that, even more spread out in terms of wavelengths, you'll end up with radio waves. So radio waves are a type of electromagnetic radiation that are just very, very large in terms of what they have for a wavelength. Now, if we look at this, the longer the wavelength is going to carry with it a few properties. The longer the wavelength, the lower the amount of energy, and the smaller the frequency. So, as the wavelength gets bigger, the frequency gets smaller, as does the amount of energy carried within that wave. On the other side of the color spectrum, we have violet, and just past violet is ultraviolet, or UV light or UV radiation. Ultraviolet is invisible to your eyes, but there are animals such as certain insects and birds that are actually able to see ultraviolet colors. Now with ultraviolet, its wavelength, instead of being larger and larger, is getting smaller and smaller. As the wavelength gets smaller, we're going to have a higher amount of energy, but a larger or a bigger frequency. Now, because this is carrying more energy, it's actually able to cause damage. So if you've heard of UV radiation or people putting on sunscreen to protect against UV light, this is what we're talking about. Ultraviolet radiation is strong enough to actually get through your skin and actually cause damage to your DNA, and that could lead to a mutation causing cancer. So skin cancer is a high risk for individuals who might go tanning or have lots of exposure to ultraviolet radiation. If we keep making these wavelengths smaller and smaller, we're going to get X-rays, which actually have enough energy to penetrate through your body, except for your bones, which allow you to take a picture or image of your bones. And past X-rays, you'll eventually get to gamma rays, which have very, very high amounts of energy and are very lethal.